In section 13, we're going to allow for a trend over time. We're going to take a look at the standard latent growth analysis, growth mixture modeling that we use for continuous outcomes. And we're going to also take a look at longitudinal latent class analysis as a flexible way of describing trends over time. And then we're going to turn to latent class growth analysis and growth mixture modeling. On slide 135, we have two of the main variables in the combined data from the alcohol treatment trial. We have stress at the top and abstinence at the bottom. And we have described here on the x-axis the baseline at week 0 up to week 16. And for the stress variable, we see that the means start high at the baseline and then go down in a approximately linear fashion with some bumps along the way. So a negative slope here. For abstinence, that's derived from the 5-category alcohol risk variable. We're just looking at being in the abstinent category or not. And nobody is abstinent at baseline before the trial starts, but then abstinence jumps up to 0.55, the proportion abstinent, right after treatment starts, and then it slowly starts going down over time, over the 16 weeks. There you also have a linear trend, pretty much, negative slope, but with a little bigger bump here in the beginning. The question now is this: can a left-out random effect, like a random slope, capturing a trend, can that distort the random intercept variance or the autoregressive coefficients? And would cross-lagged effects therefore be affected? So we've talked about how correlations across time are the building blocks, the basic information that we have for estimating random intercept variance and autoregressive coefficients. The Ri and Ar are the quantities that explain the correlations across time. But if you have not only a random intercept but also, say, a random linear slope, then that variable would also explain some of the correlation across time, and that doesn't need to be explained by Ri or Ar. And how would that affect our cross-lag panel modeling using Ri and Ar? That's the question. On slide 136, we take a look at the simple case of latent growth analysis for continuous Ys. And I'm saying that we can add linear and quadratic random effects to the random intercept, and that also contributes to correlations across time. And I'm looking at a model here, the simple linear model, with the linear slope here, eta sub 1, and a random intercept eta sub 0. This is taken from our short course on growth modeling. And here we have the usual time scores x going from 0 up to t minus 1. And if you look at the covariances between the y's at different time points, time point t and time point t prime, it consists of 4 different parts: the variance due to the random intercept, the variance of the random slope times the time scores, and the covariance between the intercept and the slope times time score sum, plus the covariance between the residuals, which is going to be captured by the autoregressive model, autoregressive parts, that is the regressions among the y hats in our new language. And these 4 terms can be illustrated visually by the pictures below here. So the variance of eta 0 is the covariance. That's the part of the covariance that's due to the covariance between time point t and t prime. So it's the variance of eta 0 times t and t prime time scores, which are 1 for the intercept. So you get that term. Second term is the variance of the slope times the time scores t and t prime. They're not 1, they are then time scores for time point t and for t prime. And then you have the covariance of the intercept and slope times xt, time score t, So that is the covariance between the two random effects. And you have then t and t prime, where t prime is again 1. Anything coming from eta 0, the random intercept is 1. So you get the first term here, xt, and here you get the second term, the covariance, times t time score, which is 1, times the t prime time score. So you have these 4 components of covariance across time. And the question here is, how much does the variance for the slope and the covariance of the slope and the intercept contribute? Does it contribute so much that the random intercept variance and the autoregressive coefficients would be distorted if we ignore it? So let me turn to slide 137, and we take a look at the fit for the RI-AR2 model versus a linear growth AR2. And since it is a continuous stress variable, we're using MLR here. And we find then that the RI-AR2 model fits reasonably well. Not a great p-value here, but the RMSEA and CFI are good. When you turn then to the linear growth model, you and we show the output for that model on our website for this web talk. You see that we have fewer parameters because we impose a linear growth restriction on the intercepts of the y outcomes over time. We let the mean across time be described by the slope growth factor mean times its time scores. But that fits quite well. It has a lower big value than the original model, and chi-square is on the border of the acceptable for the p-value certainly, but it's going to be easily improved if you allow, say, 1 or 2 time points have a free intercept. I checked that out, and you actually need only 1 random intercept being different from the linear line. So we're going to take that model as it is, as good enough for our purposes here. And then you have the input for this linear growth AR2 model. We're looking at the weeks 1, 2, 4, 6. So we have non-equidistant distances here between the weeks. And I've chosen the time scores accordingly to reflect the distances. And then I simply add an autoregression among the residuals, which is a new feature in 8.7 of Mplus, where you just talk about the residuals as hat variables, pairwise regressed, lag 1 and lag 2. So you have a random intercept, a random slope, and these 2 autoregressive coefficients. And it's of interest then to compare the MLR estimates for the RI-AR2 model on the left and the growth model on the right. If we start with the growth model on the right, first of all, we can take a look at the mean of S, and it's negative and it's significant. So we capture that downwards trend over time. And we see that the variance is substantial for I relative to its standard error, and that is also the case for the variance of the linear slope. So a linear slope is certainly needed here. If you compare with the variance of the random intercept, it's fairly similar, 5.4 versus 5.3 here, not too big of a difference, a little bit bigger here, as one might predict. What about the ARs, the autoregressive coefficients? Well, first one is lower now. Second one is higher. This is the first order I'm looking at. Third one is higher, higher, lower, lower, and here insignificant, negative, but insignificant, whereas it was significant positive over here. So they come out differently, but there's no clear trend in the autoregressive coefficients being higher on the left, as you might expect when you ignore the trend. So let's look at this model in the linear growth AR2 case for stress, and we repeat this formula that I mentioned before, but now I talk in terms of I and INS instead of eta 0, eta 1. But you have the same four terms, and instead of covariance between epsilons, I talk about covariance among the y-hats, the residuals, same thing. Except now we, nowadays we are able to do a autoregressive relationship between the residuals as opposed to the earlier days when we let the covariances just freely correlate. The estimated covariance between the observed variables is obtained from residual or from TEC4, and the estimated residual covariances are obtained from TEC4. So you find new stuff in TEC4. Now when we turn to y-hat modeling. So let's take two time points, y4 and y5 as an example, middle of the development. And here is the random intercept variance. Random slope variance here times the time scores. And I'm talking about time point S and T instead of T and T prime. And then you have the covariance, which is negative, times the sum of those time scores, plus the covariance between the residuals. And multiply that out. And then I switch from covariance to correlation to show what the parts are that contribute to the correlation. And we see then that the major part is from the random intercept, 0.5, whereas the contribution from the random slope is fairly small, and the autoregressive contribution is 0.1, bigger than the contribution from S, but far smaller than the contribution from I. So in this example at least, the contribution from the random slope is relatively small. So the results that we had earlier for the RIAR2 model may be quite trustworthy, even though we had a trend, is what one would conclude here. Now we turn on slide 140 to the analysis of a binary outcome, that is, in this case, the abstinence variable, the dichotomized alcohol risk variable. I'm going to compare the categorical model fit for RIAR2 versus the linear growth model AR2, and using base here now since we have categorical outcomes. Same time distance and same sample and number of time points. I should say that we have the outputs for these runs on the website as well. So then, first of all, we take a look at the unrestricted model for the binary, which I don't think we did earlier. We looked at the polygamous alcohol risk variable in the unrestricted case. But here, the unrestricted binary version fits quite well. We have one misfitting response pattern here. However, as it says, it's the third most frequent pattern, so it's not the most frequent at least, and the z-score is only barely above 1.96. So I would call that a good fit, so we can go on and then restrict the model into AR2, which also has a good fit, and RIAR2, which has a good fit, adding one parameter. And then we turn to the linear growth model with AR2. So in addition to random intercept and AR2, we also have a random slope. So that's fewer parameters because we impose restrictions on the thresholds. The thresholds are not not unequal, allowed to be unequal across time, but are restricted to be the same. That gets a good PPP and a good fit in terms of residuals as well. Interesting is that for model 3, the estimated random intercept variance is smaller than its standard error, the posterior standard deviation in base terms, so suggesting that the trait is not substantial and that model 2 could be sufficient. Model 2 where we don't have a random intercept. Whereas for model 4, the estimated random intercept is substantial relative to its standard error, or standard deviation. So it's quite a different conclusion here. The random variance is also substantial. Correlation is negative 0.4. Mean of S is positive, which means that the probability of non-abstinence increases over time. We saw earlier that abstinence decreases, so here we have non-abstinence increasing, same thing. The input for this linear growth AR2 model for the binary abstinence is here given for Bayesian analysis. So we have categorical Z variables and we cut them. It's a 5-category variable that we dichotomize. And we have a base estimation going on. And we have on the right the linear growth model INS with the same time scores and the AR1 and AR2 residual regressions. Now, one thing we have to remember here, since we are in the growth model situation, is to fix the residual variances to avoid growth model theta parameterization default of last t-1 free. In growth modeling for categorical outcomes, we fix only the first variance, z1 in this case, to 1 and let the other ones be freely estimated. But we don't want to do that here in this autoregressive context. That wouldn't be identified by according to the discussion that we had earlier on. Turning then to the bivariate analysis, so both processes, stress and abstinence, on slide 142. And I should mention that again we have the outputs for these runs on the website. So here now again we compare model fit for RI-AR2 versus linear growth AR2, adding the linear slope. And we're looking at both base and WLSMV estimation here for completeness. So the RI-AR2 model had a decent PPP and a good residual fit. In the WLSMV version, we have also a very good fit in terms of the p-value. So we're pleased with that model. Adding linear growth then, that is adding a random slope, we find a decent PPP and a good residual fit. And WLSMV agrees that it's a decent fit, but it arrives at a non-positive definite solution. Again, it's a not a negative random intercept and negative slope variance, but another non-positive definite reason. And also for base, we have an issue. To achieve convergence with base, the linear growth model fixes the variance of the slope of abstinence at 0. Actually, with base, you cannot fix it at 0, but at 0.1, some small value. And then you fix to 0 the corresponding covariances. And that's how this is done. So it's only a growth, random growth for stress, but for abstinence, the slope is not random, it's fixed, it has only a mean. So that's okay. But the WLSMV run is not admissible. So what do we conclude from this bivariate analysis? Well, we have agreement in terms of number of significant cross-lagged effects for the two models. The two models being RI-AR2 versus the linear growth AR2, where we've added a random slope or added slopes. The stress variable slope is random. The abstinence slope is fixed, but it's still there. Well, we seem to get agreement for Y on Z. 7 out of the 7 cross-lagged effects are significant in both models, and Z on Y is largely insignificant. The linear growth model has 1 of the 7 cross-lagged effects significant. So the conclusion is that non-abstinence has a significant effect on increase of stress, not the other way around. And that's in line with, those findings agree largely with those we had on slide 133, using the 2-part model for the 5-category alcohol risk variable, especially in terms of the Y on the ordinal part of Z. So here we conclude that including a trend using linear growth is not essential in these data from the point of view of cross-lagged effects. But it's something that's worth checking in your data sets. This may be specific to the features of these data.